Right? For planning purposes, in discussions with a client, an architect would like to understand what is required to shade a large south-facing window or large south-facing windows in a one-story building in Orlando, Florida, which is 28 degrees north latitude. What is the angle X so that the entire window is shaded on the summer solstice? So this is what we're looking at, this angle X. And so we have some kind of a canopy, some kind of an eyebrow. And that eyebrow, that louver, that canopy, that horizontal protrusion is gonna, we want it to shade the window. So we wanna figure out where the sun is up here. And then we wanna go ahead and create this. We wanna use this information to create that dimension. So I don't think there's anyone working right now who's better at kind of thinking about solar geometry as it relates to a glass ceiling as Renzo Piano. He's kind of evolved this series of glass ceilings for museums. Kind of each one seems to be a little bit more sophisticated than the last. And I love them because they're not the glass ceilings that like architecture students think a skylight should be, where they just make a giant atrium with glass and call it a day and say that's daylighting, because that's not really daylighting. We don't really want all the direct sunshine to come in. In fact, we generally want none of the direct sunshine to come in. More on that in a future 60 or 40 minutes of competence. But this is his high museum, or the addition to the high museum that the original, of course, is Richard Meyer. And in the I think Meyer built it in the late 80s, maybe it was early 90s, but no, I think it was late 80s. But but that original museum had to undergo some renovations in 2003 that had to do with daylighting. So daylighting was kind of in the front of their mind when they were making the addition. And so they just went to a lot of effort to try to get the daylighting right. So basically what we're looking at here is a ceiling, and this is where that light is coming from. So each of these is looking north. Each of these round skylights is looking north. And then there are these little, I don't know, elements. Renzo Piano calls them sunflowers, but they're not. He also concedes they're not quite sunflowers, because sunflowers turn towards the sun, and these are turning away from the sun. So the idea is to turn away from the sun. You can see the sun is hitting that there, and the idea is that we want to limit or eliminate, in this case altogether, any direct sun that might come in and either damage paintings, but also create excessive contrast or glare, or start having some kind of a stippling effect. I'm not even sure what the right word is, but an effect where you'd have kind of dots. So they built, of course, digital models, and they built bigger and bigger and bigger physical models until they got to a full-size physical model. And they discovered that in the mornings, sometime around 10:30 to a little bit before noon, maybe 11:45, depending on the day of the year, there was some direct sun coming through. So they applied a frit, a custom frit. So a frit, of course, is a ceramic paint, and often, and I'm not sure how it was applied here, but often it's applied in a dot matrix pattern to like 40% opacity or 30% opacity or 20% or 50% or whatever. It's the same type of frit that I put on my house, for those of you guys who are familiar with the glass element on my house, the bubble wrap edition. So anyhow, that was to shade the light, shade the direct sun on those few hours every morning in the summer where the light was coming in. Now, this is, like I mentioned, kind of a long-term project for him. Famously, his father was a builder in Genoa, and so he's always been very kind of cognizant about building and kind of taken the detailing of this quite seriously. And I recommend for any of you guys, just kind of look up, if you can find it. I found it online. Look up how he details each of these, because it's really interesting and how it's evolved. In part because just how the hell do you keep leaves from building up on it and drain the water? And custom skylights are not easy to keep tight over long periods of time. This is the Menil collection. I think this is his first attempt at this, and so it's in Houston. And it's a museum like all the others, and this is kind of his sketch. And see, there's a place for the water to run out and then into a gutter. And when you're in Houston, if you're in anywhere, we're talking about overhead light, but especially in Houston, you need a way to shade that light, because again, you don't want the direct light coming in. So the idea is that the high summer, southern sun comes in and bounces off this and bounces off this, and you get kind of a double bounce. And the effect is something like this. So this is the way we want a daylight. We don't want any areas in the room that have glare, that have too much sun coming in, and we don't want any areas that are too dark. So this allows a diffuse light to come in all the way. This is by far the single thing that architects don't know that they should. It's not huge for the test, but you should know that daylighting is not about bringing in more light. Typically, occasionally it is, but it's more about bringing in light to the darkest places in the room and shading the direct light on the perimeter. All right, so here we have it again. This is the Menil collection, and here's what it looks like from the outside. And then we have the Byler. Actually, this might be the Byler too. Here we have the Byler in Switzerland. It's in Basel. And this is also kind of his next attempt. I think I have the order right. This is his next attempt. And again, you see some way to kind of start to think about layers of glass that one might be for, kind of taking most of the water mechanically and directing it, and then elements underneath to allow for true enclosure. And so this is what it looks like in Basel. And then like the Menil and like the other museums we're going to see, the transparent or translucent roof extends beyond the enclosure and becomes part of a kind of a 3/4 space. And what is better architecturally than 3/4 spaces, whether it be a courtyard that has a wall and a floor but no ceiling, or in this case we have a kind of no floor and we have a ceiling. Sometimes we have a wall and a ceiling and no floor. Sometimes we have a ceiling and a floor and no walls. You get the idea. But these are, I think some of my best times I've had in my life are on, kind of in these 3/4 spaces. And man, I wish architects would make more of them. All right, so this is again the Byler, and here you can see the layers that are for mechanically redirecting most of the rain, and then underneath it, just a little bit of the rain gets through, and then that's where it goes to these channels that also serve as the structure. The primary structure and the secondary structure comes across in a grid, and then it lets some of the light through. I thought these were people at first, but then I realized they're not. So part of the art. And again, here's what it looks like on the inside. This is the Nasher Museum in Dallas. Also Renzo Piano, of course. Many of you guys have been here. It's a sculpture museum, and this one, he starts to. This is the partie section, and he's got these cable stays that hold up the middle, and then there are these bays, and then again we have a transparent or translucent roof. And here's where he starts kind of messing with the trick of looking north. So he's looking north, and here you see those cable stays holding up the middle of the span, and he's looking north with each one of these, and that's what it looks like from the inside. But then, I've seen this photo everywhere, and it's funny because these photos, it's actually not funny. It's really quite, I think, damaging to the profession, because these dramatic photos with direct light coming in always kind of make the magazine covers, but it's really not what we want. We don't want direct light coming in. We would much prefer, if there's going to be direct light coming in, we want it to be electric light, kind of focused right on the art, and we want ambient light to be provided with diffuse light. And so here is this kind of stippled light that I was talking about, and here it is close up. And again, I think it's promoted here, my guess is, by the photographer as this kind of great inspiration of the architecture and the art. But in reality, first of all, it's probably only like this a few hours a year. But second of all, this is not what we want. It doesn't mean it's a failure if we have it, provided we don't have it for too many hours a year, because it's cloudy a lot and the sun's always moving around. And so our goal is generally not to provide perfect lighting all the time. Our goal is to provide really good lighting almost all the time. And we're not going to sweat it if once in a while there's a little bit of direct light coming in, unless you're the High Museum, in which case they did sweat it. And then this is finally, this is Piano's addition to in Fort Worth to Kahn's Museum. And so again, you see there's these kind of layered elements where we're thinking about structure, and the structure is often where the rain is going to go at the primary structure, and then the secondary structure spans across, and supports some kind of a mechanical layer that sheds rain and then and probably leaves and probably can be cleaned pretty easily, I would hope. And then, but beneath that is the actual enclosure. And then again, we have an element that comes out beyond the building to create a 3/4 space, although I would argue maybe not the most successful 3/4 space spatially. And this is what it looks like from above. And again, you can see some of the shading elements and that are incorporated in some of these. And from the inside. And of course, Renzo Piano was a mentee of some kind of Kahn. I'm always kind of confused by how much that was. I've certainly seen this picture, and there's one other picture that I've seen floating around of the two of them together. But I don't know how. Kahn was certainly influential in Piano's life. I'm not sure how, I'm not sure if Kahn recognized Piano's potential back then. But Kahn, of course, did the original museum in Fort Worth, the Kimball I've been talking about. And he has these skylights, he put these skylights that exposed to the high summer Fort Worth sun. And the light's going to kind of come in, but we don't want it to come directly in for all the reasons we just talked about. So it's going to come in and it's going to bounce off, and then it's going to go down. And so it's going to wash these centroid barrel vaults and come down. So it looks something like this, where here's the skylight and the light comes in, and then here, and then, well, it kind of washes like that. All right, so let's talk a little bit about these charts, because they're a little bit tricky to read. Even if you've done it a few times, it takes like, I think 5 or 6 times to do it. So, when you're done, you can take a screenshot now on your phone or on your computer, and then you can do it later and kind of play with this a little. You can check, where's the sun on your own birthday? And you can check, where's the sun on your mother's birthday? And so forth. But what we have here is we have a solar path diagram, and there's other versions of this, but this is the version the exam likes to use. There are other versions of using kind of a graphic to determine where the sun is, and generally we think that the sun is. Well, let me hold on. I'm going to pull up some software that I don't think I shared with you guys. So this is a great app. So you can put on see, it's telling me where the sun is in my room. So I can see the sun is over there. But I can also see the path. The red line is the path, 8 p.m. on June 20th, 7 p.m. on June 20th, 6 p.m. on June 20th, 5 if you look at the red line. If you look at the green line, that's the solstice, that's the equinox. So on September and March 22nd, we can see where the sun is in the room. And then you can see in the winter on December 21st, you can see where the sun is. So you can go to a site that hasn't been built yet, and you can see where the sun is with that app. It's called Sunseeker Pro. I would definitely pay the $10 to get the Pro version, because then you can go to a renovation and you can say, what if we put a hole in this wall? Or you can go to a site that hasn't been built yet, and you can see exactly where the sun's going to be at different times of the year. And you can say, let's punch a window here, or let's put a skylight there, or let's, if we put a skylight here, it'll wash this wall. So let's make sure to get a great texture on that wall to account for the grazing light. Anyhow, so generally these days, if you want to figure out where the sun is, it's done in the software, right? So within Revit or within whatever tool you're using, the app is called Sunseeker Pro. Yeah, it's amazing. I gotta tell you, I have it on I first put it on the iPad, but then now I have it on my phone, and I'll pull it up all the time, and I'll be like, oh, where's the sun? Where would the sun be? If there's like some glare that I see, I'll say, okay, where would the sun be? Is this just a today thing, or is this an everyday thing? And you can kind of just look and see. It's really fun. Anyhow, go technology. But this type of sun path diagram is the one they use on the exam, and it's not super intuitive to read. And so what we're looking at is we're trying to find out what is the azimuth of the sun and what's the altitude of the sun. And so the azimuth is, if you were to spin around in your chair right now, and you could only hold your arm outward, what would be the kind of in plan, which direction would the sun be? And the altitude is in section, how far up off the horizon would the sun be? So if we say, if this is me, and if the sun is, over here, then I might say that the sun is in plan. I might say that the sun is 30 degrees west of south. That's the azimuth. And azimuth is spelled A-Z-I-M-U-T-H. And then the altitude is, okay, in section, here's me. And then here's the sun. And so the question is, how high is the sun in the sky? And maybe it's 32 degrees up in the sky. And of course, the sun is going to move. I hate the way architects do daylighting really poorly. I got to say, there seems to be this belief that the sun is always like at noon in the winter and in the summer, and the two solstices. But in reality, of course, the sun is always moving. It's only there for a little while. It's in the west and it's in the east and it's overhead a lot of the time. So it's not just in the south. That's nuts. It's on the east and the west a lot of the time, and it's overhead a whole lot of time. In fact, it's overhead a whole lot more than it's in the south. So the roof gets way more sun than a south wall does over the course of the year. And even in the, only in December for a few weeks in December, depending on your latitude. But anyhow, the sun's position is going to, of course, change by time of day, but it's also going to change by latitude, so where you are in the world, and what month it is. So this takes all of that into account. This is the sun path diagram for 28 degrees north latitude. They publish these for every 4 degrees north latitude. They probably have computers now that can create them for any latitude, because it's all just complex math that computers are good at. But generally, if you look in a book, you'll find it for 16 degrees, 20 degrees, 24 degrees, 28 degrees, 32, 36, and so forth. And so Orlando is around 28 and a half, and I don't know, Philly is probably around 32 or something like that. So that should give you an idea of the kind of the span of what 4 degrees latitude is. And so what we're looking at is these circular numbers, these circular lines that go like this, these concentric circular lines, one after the other. They describe the altitude of the sun. They describe how high the sun is in the sky. So 10 and 20, 30 and 40 and 50 and 60 and 70
Espérame.
and 80.
Yo estoy en clase.
I'm going to go ahead and...
I'm not playing. Yo ya ahorita te voy a revisar tu tarea porque yo...
Mama, why there?
Okay, there we go. So that's the altitude, these different heights, or these different numbers in the concentric circles. And the azimuth, where the sun is in plan, is 10 degrees east of south, 20 degrees east of south, 30 degrees east of south, 40, 10 degrees west of south, 20 degrees west of south, 30 degrees west of south, and so forth. And those are these lines that go like this. So the question is, now that we know that, where's the damn sun? And that's where these other darker lines come in. And it's super confusing because the months are usually marked in Roman numerals rather than letters. And I don't know if that's so it works in every language, or so that people in Australia or Argentina can kind of work with this a little bit more easily too, because obviously the June and December there are swapped. But we have December is this 12th month. So here is the line for December. And then November and January, and each of these lines is for the 22nd of the month. So January and November are the same. So January and November, the sun takes the same path. So this is XI is November, that's 11th month. And I, Roman numeral I, is the first month, January. And then here we have February and October. So February and October look like this. And here we have the equinox. So the equinox looks like this. And so forth. And so this is March. The equinox, of course, is March 22nd and September 22nd. And so the question here was looking at the solstice, specifically the summer solstice. And in the summer solstice, we're talking about June 22nd. So we're talking about VI, or the 6th month of the year. And it's going to be this line, oops, right here. Well, I didn't quite do it right, but that's because I purposely didn't want to obscure the numbers. So the real line is actually going to be right about here. And these numbers are the time of the day. So this is 7 a.m. and this is where the sun is 8 a.m., 9 a.m., 10 a.m. So right now it's pretty close to it's probably a little bit closer to August 22nd. So we'll say it's August 22nd today. And right now here on the East Coast, it is about 6:30. So what we can do is we can see where the sun is right now. So let me see if I can change my color a bit. All right, so the sun right now, it's 6:30. So let's say it's 5:30, just to make it a little clearer. So it's going to be somewhere between 5 p.m. and 6 p.m. And this, of course, is in Orlando. So if you're in Orlando, you can know where the sun is. Of course, you can know that anyway by going outside. And we have this March and September line. We're doing August. This August and April line is going to be right here. So if it were 5:30, which it's not, but let's say it was 5:30, we can see where 5:30 meets August 22nd, and the sun is right here. All right, now the second question is, now where is the sun? Well, it is actually about the azimuth of it, interestingly, is in the north, in the northern hemisphere. It's 10 degrees, no, it's 5 degrees, 5 degrees north of west. So it does go in the north sometimes. The sun does go in the north for a small portion of the year by a little bit. And that's its azimuth. So if we kind of, plot you in Orlando, and this way is north, and this way is west, the sun is kind of 5 degrees north of west. And then to figure out the altitude, well, we have 10 degrees, 20 degrees, 30 degrees, and so forth. And so we see here that this first line along here is 10 degrees. So it is 10 degrees. It is 10 degrees up in the sky and 5 degrees north of west. So it's obviously very low in the sky because it's near sunset, at least in solar north. Now, this doesn't account for, this doesn't account for so many things, because really what we're talking about is we're talking about where the sun is. And we're saying, okay, but you can say, Ermin, this doesn't, like, who cares? Because this is only for 1 minute a year, right? And I think that's a really fair criticism, except it's okay if a little sun gets in. So what you want to do, if you're doing something like this for your project, you want to say, okay, I want all, in this case, they're saying, I want all of the windows shaded when the sun is noon and it's as high as it can be, basically. And that means that on the solstice, on the June 21st, that's at noon, but at 11:59, some of the sun's getting in. And at, at 12:01, some of the sun's getting in, and it's certainly getting in at 10 and 3. There's certainly lots of sun getting in, but the goal is we want to shade most of the direct sun most of the time. Now, one other way we can do that is, we need this glass for view, and we love this glass for bringing in light deep into a space, because in the wintertime, it goes deep into the space. But we really usually don't need glass below, hip height. 3 feet or below the glass, it gives us that great feeling of being in a perch, which is really architecturally, I think, worthwhile. But from a daylighting or a view, and certainly from a heat gain and heat loss perspective, we don't need that glass. It's not really benefiting us. So that's one way we can deal with it. It's just kind of, we could not let the sun in on the bottom by essentially moving the bottom up. But it's not that big, so you set a goal for, sometime in the summer, pick a morning and an afternoon, pick 10 a.m. and 3 p.m. in July, and pick 10 a.m. and 3 p.m. in January. And then just decide, do you want the sun coming in or not? And that'll help establish a maximum or a minimum or both dimension of this guy here. And so what we have on our particular situation is we are looking at noon. So noon is going to be right here. It says, 11 and 1, but obviously we're talking about noon is right down the middle, because the solar noon is going to be due south. We're talking about the 6th month of the year. We're talking about the summer solstice. So it's going to be here. So the azimuth is going to be due south. It's just due south. And then the altitude, how high it is in the sky from the horizon, is going to be, well, it's going to be 10, 20, 30, 40, 50, 60, 70, 80, almost 90. So we'll call it 85. So if you were plus or minus 3 degrees from 85, you got it right. Congratulations to you. So what does that mean? Well, as always, don't just look at the numbers. The numbers are meaningless. I'm much more interested in you understanding what it actually means. And it means that the sun's almost directly overhead in Orlando in June at noon. And so this is what we mean by the altitude. We're talking about that angle there. And it's going to be pretty high, relatively high in the summer. And then in the wintertime, it's going to be relatively low. That angle, that altitude is going to be a lower number. So you definitely want to have a kind of a sense of that. And so what we can do, like we do at the Met, is we can say, okay, given that the sun is not really in the north, we can open up a whole bunch of windows. We can put a bunch of windows facing north, and then we can get a lot of daylight from clear sky if there's no sunshine in it. So we don't need direct sunlight coming in. This is, again, something a lot of architects don't seem to kind of grasp. We don't need any direct sunlight typically. And we actually don't need windows this big. We can usually do it with something like, 15%, 10, 15% is usually enough if it's well placed. What do I mean by 10 or 15%? I mean of the floor area. So if you have 100 square feet of floor area, 15 square feet of window will typically do fine if the window is correctly placed. And so we want to have, especially in hot climates for small buildings, we may want some direct gain. And oftentimes what we want for direct solar gain, which is the sun coming directly in, is not what we want for daylighting. Now, again, NCARB doesn't seem to know, because I think most architects don't know, and it's architecture volunteers and not building scientists who are making these exam questions. NCARB doesn't seem to know that we don't want direct sun. So you can ignore that, but it's just very important to me that you know that for your career so that we can have better daylit spaces, because we're really screwing that one up as a profession. So we can bring in deep sun, and we can do it geometrically in plan. This is my favorite. We can start to think about the reflectivity of the outside surface, and of course we also have the sunlight coming in here, and we have the sun bouncing off these surfaces to maybe bring in some bounce light. But we can stagger it in plan. We can stagger it up on a hill. So again, these high windows are really good because they bring the light deep. They're not good for view, and view is important as well, but they're pretty good for daylighting. And daylighting and view are separate. They're related, but they're separate. So we can do some kind of a sawtooth roof monitor proposition. We can put a mezzanine, and then we can maybe even put a tray, like a mezzanine tray under a roof monitor. Roof monitors are great because, and they're totally underused, because they have vertical glass. We can angle it to the south or the north, and so we won't get much unwanted direct sun coming in. North is generally better from a daylighting point of view, but we can angle it here. It's angled to the south, but we can angle it to the north or south, and we can bring in light, but most of the time we'll be seeing the sky, and we're bringing the light in deep into the space. So if you are on the top floor of your building, or if you have a one-story building, think about roof monitors or some kind of vertical glass on the roof, like this. So again, high glass brings deep daylight. And like I told you, this one's not intuitive. I wouldn't, if you gave me 6 months, I probably couldn't have come up with this very simple seeming section as a way to bring light deep into a space. But again, high windows and roof monitors seem to cure everything. And so generally we want to think about where the sun's going to be, and then use solar geometry. Now this one I don't love. I mean, this kind of glass, this is because this is the kind of simplistic thinking that if we just bring a lot of light in, then that'll be good daylighting. And in reality, that just brings a lot of solar heat gain. This thing becomes especially in Orlando, it becomes a greenhouse during the whole year. But even in other places, it would become a greenhouse. And then when the sun's not out, like at night, the thermal resistance, the R value of the glass, is probably something like 1/10 or 1/20 the R value of the opaque roof. And so we're losing, 10 or 20 times per square feet the light. Oh, it is a diagram of Harvard GSD. You're right. Boston's of course a little colder, but that building might have been built before the energy crisis. So go ahead and answer this question. For a warm climate in the Northern Hemisphere, vertical fins are most appropriate on the blank side of a building, north, south, or west. Go ahead and answer it to yourself. So this should be a pretty easy question for most of you. And you did all seem to get it, because generally what you were taught in school is that we want to elongate the building in the east-west dimension. And because we kind of believed, I think erroneously, that the sun was almost always in the south, but okay. And so in the south, if this is planned in the south, and the sun's over here, but the sun is going to be really low in the sky. So in section, we have the sun coming down at some kind of an angle, and so we want to extend an overhang on the south, and that way we can keep out the high summer sun and we can allow in the low winter sun. I think all of you guys probably kind of got that. And one of the things I see all the time is I see people, they do this, they say, okay, here's the angle from the top, and then there's the angle to the bottom, but the sun comes from the same angle. Don't get confused between your diagram and reality. So in reality, the sun would not be coming like that. It would be coming like this, where this line and this line are parallel. Of course, as the sun's rays are parallel, they don't vary by 15 degrees just because that's how much room you have to the left of your slide to put a sun. The sun is very far away and very big relative to the Earth. So its rays are, for all intents and purposes, parallel all the way across the Earth. So, but in the West and in the East, the sun is often very low in the sky. So the sun is often very low in the sky. So we say, okay, it's low in the sky. There's no overhang in the world that can be far enough out that can prevent this kind of really super low sun from coming in. Of course there is. I mean, it's always a few degrees up, but it becomes an untenable solution. So what do we do? What's a boy to do? Well, we can plant trees here. That's a pretty good one. And frankly, that's probably the best. But often what we can do is we can put, and if you get this question, a question about this on the exam, we can put vertical fins. So now I'm drawing in plan. We can put vertical fins on the east and west if we have glass there. And that way, because the sun isn't really due west most of the time, okay, it is for a little bit, but it's usually a couple of degrees south of due west. And oftentimes it's more than a couple of degrees south of due west. So a lot of the year, it's maybe 15 or 20 or 30 degrees south of due west in the afternoon. And so for that reason, we have the afternoon rays coming in like this. It's low, but they're coming in plan, they're kind of coming in at an angle. So each one of these is shading the glass. Now, the downside to this, and it's a significant downside that is not discussed enough in architectural circles, is that you really can't see out when you put these vertical fins, because you're never, unless you're right here looking out, if you're here, you can see straight through, you can see straight through here. But anytime you try to look to either side of the window, a lot of your view is going to be blocked, where you just can't see out because of the fins. If they're close enough to keep the sun out, they're also going to be close enough so that you have this window there that brings daylight in, which is good, but maybe doesn't allow view out, which is also important. View we found to be highly correlated with performance in certain arenas. So anyhow, we want to bring in this, overhead light, and these are what I mean by roof monitors. We mean something where we have vertical glass. This is kind of an atrium regime, and and this is a skylight regime, and we prefer in most cases not to have that if we don't have to. We prefer vertical glass high up, and that brings light deep into the space. And so I was running one day by this building, and I was so excited. I was like, this is the coolest building. And I went inside, I knocked on the door, and they let me in, and they said, oh, we haven't had a visitor in years looking at the architecture, because I guess this one won some state AIA awards back in the 80s. But what we're looking at is we're looking at roof monitors, and these are very specific roof monitors that are based on the solar geometry that's present in Fairfax, Virginia, or really almost anywhere in the U.S., where we have the sun coming from the south. So here's the south side. So you see the sun kind of shining on this surface, and so the sun's going to come in. It's going to come in here. It's going to bounce off this wall, which is white intentionally. It's light colored. Then it's going to bounce off this surface here, which is also white, and it's going to go down into the building. And then there's actually glass that sees the north sky right here. You can't see it, but we'll see it in a second. So when you're inside, you can look up and see the north sky, and you can look up this way and you can see the reflected light from the south with the double bounce. And it actually, at one point, briefly had a green roof. This is one of the reasons I happen to hate green roofs, because roofs don't want to hold water. They want to shed water, but plants want to hold water. And so they put a green roof on here, but then it was leaking. And of course, it's one thing to get a client to accept the green roof, but it's another thing to get a client to put the roof back on after leaks are found and to kind of replant the roof. It's not likely to happen. Now, albeit this was in the 80s, and we have come up with way better materials and systems and details for making green roofs than we had then. So it's way less likely to leak now, especially with extensive green roofs where we have trays rather than intensive green roofs, which I think is what this was, where we actually just are planting the roof like it was a lawn. But anyhow, and then there's these overhangs here on the south side, and they're louvered. They're like pergolas, and that's why we always see that in like, you know, the Caribbean, because we have a place for the heat that might build up there to get out. But again, see here, you see the south facing glass, it's vertical. Now I went inside and I took a photo up, and I can see the sky. So I'm looking at the north sky right here. That's the north sky. But see, there's a significant amount of light coming from the double bounce from the south roof monitor. And here is that north glass looking up. And then I thought I was so cool that I found it. And then I thought I was double cool when I saw it published in a book. And so here again, you have that diagram. And then I saw it published in another book. You guys recognize these sketches from these drawings from Sun, Wind, and Light. Fantastic book that I highly recommend, that confuses people, but yeah, maybe I should do a whole 40 minutes of confidence in how to read the 3rd edition of this book, because that does throw people for a loop. But anyhow, but this is the diagram from that. And there's also, I didn't know that, but I didn't know that when I visited, but there's a way to, you know, evacuate the warmest air. So the warmest air is coming up, and they can use this as a stack effect cooling device as well. All right, this is one of our last few examples of solar geometry in action in architecture, again from Sun, Wind, and Light. And this is a school in Fresno, California. And what's interesting about this louver system, this overhang system, is again, it lets the warmest air kind of go up and not build up and actually escape. But also, you'll notice that the dimensions in here are bigger than the dimensions between the louvers here. And so what's happening is, it's a recognition that the sun is high in the summer, straight up. And so because it's high, if you can picture the geometry of this, and most of you can, because well, you're architects, you can picture the geometry. If you have high sun, you need louvers that are close together to be able to provide shade. But if you have low sun, in the wintertime, for instance, where you'd want these louvers to stick out, where it's low sun, then you can actually have an increased space between the louvers and still provide the shade. This is also very creative. This is a school in England, and I think there's like a park to the north with a bunch of trees, and the sun of this way, of course, is south. And so you have a traditional, more or less traditional, shading element with louvers on the south side to provide shading for these windows here. But it's a little different in that there's, I'll see if I can find a photo of it. There's actually perforations in the shading element. So the shading element itself is fairly bright. the shading element itself is fairly bright. So it's not, when you're looking out the window and you see everything bright, but then there's a dark element. Those of you guys who took the Amber book know what I'm talking about. It feels, it actually makes the room look darker if you see a dark element in the same field as a bright element. So the bright window and the dark overhang would be that situation, but they let some of the light through the shading element, and that provides for a light element on a light element. But the most interesting part is on the north side, the louvers themselves are angled to actually, they're silver, and they're angled to reflect the winter sun. So when the sun is low in the sky, it comes over the school, and it bounces light back into the school on the north side, which is super, super clever. And then of course we have heliodon. This is a complicated one, but there's a really, in heating, cooling, lighting, you can just make your own with a sundial, and it's super easy. I cannot tell you how quickly you can make really intelligent design decisions building a really rough model on a sunny day with a model that'll take you 3-4 minutes to build. I mean, sorry, with a sundial that'll take you 3 or 4 minutes to build. And well, anyhow, that's a different day. Now, there were questions. Well, first of all, one of the questions I see a lot, one of the confusion I see a lot in the forum or in the Facebook group is people are often confused because some of the literature says that you should shade the north. And they think that there's conflict because some of the literature says you should not shade the north. And I am here to tell you that number one, you should not shade the north. You don't need to. And number two, there is no conflict in the literature. So if you've been kind of reading these books, you're like, how can there be? How can some say you should shade it and some say you can't? Well, I would say that you have a failure to kind of be okay with positive ambiguity, because you generally should not shade the north because the sun is hardly ever in the north. So if you can put shades on, but you're keeping the sun out just a few hours a year. But the sun is on the north. We saw it in our example at 5:30 p.m. on August 22nd or August 21st. We saw that we saw in our little diagram that the sun was actually 5 degrees. Remember, we saw it was 5 degrees north. It was 5 degrees north of we saw it was 5 degrees north of west, which means the sun does get in the north, but it only gets in the north during these hours, and only, of course, when it's sunny. And frankly, during those hours, it's not that hot. It's, the sun is not that strong. It's just before, it's, often minutes before sunset. So you don't need to shade the north in almost every situation. But if the goal was to have 0 direct sunshine coming in, then yes, you would shade the north. So one book is telling you how to get 0 direct sunshine ever in, but the other 2 or 3 books that you'll use will tell you that you don't have to shade the north because there's almost no chance of it being an issue. Now, someone also asked last week if I could cover the kind of how to figure out where it is. And this is very much in play on the exam, is how to figure out where the sun is relative to the latitude. Actually, I'm going to do that. I'm going to make a new problem for that next week. So next week, we will figure out where that is, because I want you guys to struggle with it a little bit. I think you'll remember it better if you kind of try to figure it out on your own. And we'll do it next week. So I'm going to probably change next week's question from what I'm about to show you. So we'll go ahead and skip this, because I think this is probably a 40-minute conversation in itself, kind of figuring out how to if you know what the sun is in Orlando and it's the solstice, and it's noon, you actually can fairly easily figure out that the sun is 85 degrees above the horizon. All right. And then there are lots of times where where the solar geometry becomes a glare issue, right? So, because generally there are 3 things that you need to know about daylighting, and they overlap a lot. And one is, so let's make a Venn diagram. So this one is, where is the sun? That's what we're talking about today. That's solar geometry. And then this circle is This next circle is, so where's the sun? This next, so it's the solar geometry. The next circle is how much sun is coming in. So, how big are your windows? And the third circle is glare, which is the most important one that we don't deal with, which is how much brighter are the bright areas of the room than the dark areas? Because if they're really bright, that's where the human physiology comes in, and our irises kind of start to close down over our retina. So if we see something really bright, our evolution has made it so we don't want to burn our retina. So it kind of closes down and lets less light in. But that makes the dark areas look even darker than they would have otherwise. So now talking about the kind of the wear and the glare, we know that light off a shiny surface will reflect such that the angle of incidence equals the angle of reflection, or you can put it from here or here. It doesn't matter. And so if we have a glass protector on a wooden desk, we have this kind of dark area, and then we have this ridiculous glare coming in our face. We've all been in this situation. We've certainly all been in this situation. So as we use computers more and more, I think we're probably a little behind in how we think about daylighting when our screens are often going to be facing a window. And then I don't want to focus too much on this, but I actually kind of want to focus on it a little, just to maybe make it go away. But I think there's probably a little bit unfair criticism of some really high profile architecture elements that have, this is obviously the Disney Concert Hall, and there's this one place where it's got all these concave curves, and like several blocks away, there's a handful of apartments that face it, and it's LA, so there's a lot of sun, and so the sun comes and it focuses. I'm not sure if it's that surface, but it focuses, and it sends that light and that heat several blocks away, and it focuses it. And it got to the point where there were there were several apartments that would increase as much as 11 degrees in just a matter of seconds, because the sun would hit it just right, and it would be like a solar oven. And I think probably Gary was ridiculed maybe a little bit for not thinking of this, but that's crazy. You're going to do a bunch of crazy concave curves in a sunny climate. It's impossible to think about every possible, the sun's always moving around, and it's impossible to think about every possible negative impact of that. And then we'll kind of finish up back at the Nasher. So we're back at Renzo Piano's. And so there's this garden here, and they built this tower near it called the Museum Tower. And it reflects light at certain times of the day into that garden, and make it so apparently it's almost uninhabitable. But of course, it's Dallas. It's often uninhabitable outside. So anyhow, I just think it's funny that all of the examples of that you always hear about this kind of like, how come they didn't think about it, always seems to be around some kind of a famous building. Good night, get licensed.